So, my dear viewers, welcome you all here, and this is my class on FEM. So, in general, we solve many of the problems where the shaft or beam that are subjected to different physical conditions, right? So, here we are taking one example where the bar or where the element that is with a column of mild steel. So if I draw here, you can easily understand. So here there is an one block like this. Okay, and it's an block, and above that having one more block which is at the top of this, right, like this. Okay, so it's and one end is fixed. This floor end is fixed here, and load is applied at the mid of this, at the top one. The load is applied of having 1000 Newton, and some other parameter I will going to write here. The length of each element, the length of the top one, that is 100 millimeter. Okay, all dimension are millimeter. Then the bottom one, it is again 100 millimeter, and this width, okay, from here to here, it is 10 millimeter, and this another side also 10. So 10 into 10, and here this is 20, and another side is 10, from here to here. Okay, so here what happens, in general we have taken for many of the problems in the frame that are subjected to a circular cross sections. Okay, but this is a special case where the cross section you have to calculate, because it's a square, or sometimes it's a rectangular. So based upon that we have to calculate the area, then we can proceed with the FEM procedure. Okay, so here also you need to find the nodal displacement, that is, we can say displacements at different nodes, and also we can calculate the reaction force. How to calculate the reaction forces, okay, and stress strains for both the elements, and there is a value of Young's modulus for the both material. It is given in the question. So value of Young's modulus is, that is equal to 2 into 10 power 5 Newton per millimeter square is the material property or Young's modulus for both the materials. Okay, you can say where E1 and E2 are same. So now let me say this will be the element 1. Okay, the top one will say this is the element 1, and the base will be element 2. So there are two elements now. Okay, all the procedure will be same except to find the area, cross section area of each element, that is a little uh, different as compared with the others. So that's what I just want to share, how to calculate the area here and how to proceed with the problems. After that you have to follow any of my video, then same procedure you have to follow. Okay, only that thing I want to tell you. Okay, so first let me calculate the area for element 1. Okay, for element 1, So area will be, let us say A1. So area for this element, it is the length into breadth. Okay, L into H or L into B, anything you can take. So 10 into 10, so it is 100, and unit will be millimeter square. That is the area for the element 1. And you will have the length. Okay, you require length to calculate the stiffness, that is here, that is 100 millimeter. And area Young's modulus value E1 is equal to, again, 2 into 10 power of 5 Newton per millimeter square. No need of any converting the units because all are in millimeter. Okay, all are in millimeter. So this is for element 1. Now after calculating the element 1, we'll go for element 2. Say A2, here for this element 2, that is 20 into 10. Okay, so it is 200 millimeter square. Then L2 is, again here, this is L2, 100 millimeter. What is given value, that you have to take. Now E2 is equal to, again, 2 into 10 power 5 Newton per millimeter square. So to calculate the stiffness matrix, the formula is, okay, from here onwards you have to proceed. Okay, K1 is equal to, the formula will be A1 E1 by L1, 2 into 2 matrix, 1 minus 1 minus 1, and displacements are here 1 2, and here again 1 and 2. So this is 1. Similarly, you have to write for 2, that is A2 E2 by L2, 1 minus 1 minus 1 1, and connectivity will be 3 to 4. Okay, sorry, U2 to U3 connectivity, U2 U3 for element 2. And later you have to go for stiffness matrix, that is global stiffness matrix K, you have to assemble. Then after that, apply the finite element equation, that is Ku is equal to F. So once the finite element equation you have written, then you have to go for applying the boundary condition. So that also I will tell you how to calculate the boundary, how to identify the boundary conditions. So what will be the boundary conditions here? Anyone? So boundary condition will be here. This is a fixed end. It means we have taken this as node 1, this as node 2 and node 3. So node 3, it means the U3 is 0. That is the first condition. U3 is 0 because it's a fixed. Okay. And next, the value of load. The load is applied at 1, and that is maybe 1000 Newton. 1000 Newton the load is applied. Okay, so these two are the boundary condition. Apply these in the finite element equation, then you are calculating the value of U2, U1 and U2, and U3 is 0. Okay, so from this solution I want to share this result. For U1 it is 75 into 10 power of minus 4 millimeter, whereas U2 it is 25 into 10 power of minus 4 millimeter. These two are the displacement, nodal displacement. Okay, so like that, anyhow, all this procedure I have explained in many of the video, just you can go through. Okay, and these are the result. And anyhow, reaction forces, it will be opposite to the applied forces. So our reaction forces, it will be at node 3 because the node 3 is fixed, so there will be reaction force. R3 will be we are getting minus 1000 Newton. Okay, opposite load. Okay, that will be oh, reaction force, or you can just pick up from the matrix where third row. Okay, third row you can just pick up and substitute the value of u1 and u2, so that you are getting the value of f3. Same procedure. Okay, so that's it. Anyhow, thank you for watching.